Um, we're going to talk about different fracture sets, what connectivity might look like, how well orientation can affect what we see in a particular upscale view of that, and also think about what that means for stimulated rock volume, or SRV. Um, the example I'm showing is from the late Cretaceous. It's called the Mowry Shale. It's an outcrop in Wyoming, which is a kind of the Rockies, northern Rockies of the United States. Not as important, but I will give you a little background just for that. So Lake Cretaceous, there's a large western interior seaway. There's a lot of big open oceanic marine deposits that occur in that. This deposit, and then we have the Rocky Mountain uplift. So these dark green areas are mountain belts. We're kind of out a little bit higher elevation, but not super elevated. And there's an anticlinal structure here called the Alcova anticline. It's a fault propagation fold. We're in the synclinal axis of that, kind of the flat part of it here, and that's the outcrop we're going to look at for our example today. And the only reason I say that is because the deformation here is relatively minor, relatively speaking, to the fault propagation fold area. This is sort of a back limb, so it's uniform and it's minor. That's an important parameter. We start thinking about what's the relevance of the outcrop we're looking at. So that's where it's located at. So what we've got here, I'm showing, and this scale bar is 0 meters to 4 meters. So it's just just a few meters long, but this is the outcrop exposure. And so this we took through using a drone, and so that allowed us, it's on like a tilted hill, but allowed me to do an orthographic viewpoint. Helps eliminate the distortion. And then I put it here as a complete geotiff. That's all put inside that, so I can use all GIS tools to map at a very high resolution. And the photographs here show kind of this digital resolution at the millimeter to centimeter scale. And I've traced the fractures and imported them into FracMan. So that's a commercial tool for fracture to use it for further investigation. So just to give you an idea of the level of detail we're looking at, here's a box. We're going to zoom in. Maybe it's 3 meters by 3 meters. I'm looking at that in detail. Oh, that's the image is very crisp. I can do a lot of mapping inside that. That's 1.25 meters for scale. I can maybe pick even up another box, and then it's still pretty high resolution down to this scale. And as we see, each time we zoom in, we get a little more detail of fractures that might be present inside that. So we have some larger through-going fractures in the pavement, and then some very small ones in this example. I'm going to largely take into account for this exercise. Not saying we won't discuss the relevance of an outcrop for a reservoir, if that's a really good thing to do or not. Mostly, I just want you to have a thought process as we go about that. So in this photograph, it's also important because we're going to start talking about orientations. If you notice this right side of the photos, I've rotated north to make it fit on the slide better, but north is to the kind of angled like this. So these are actually northeast. These yellow ones are northeast oriented fractures, and these red ones are north-south. They're almost parallel, subparallel to the north arrow. So I'm going to call that northeast set, north-south set, and then there's the connectors in here, which are this northwest set, roughly speaking. Again, nothing too exact, but I just want to make sure that you can see that there's 3 different sets in here, and we're going to deal with those as we go through that. Okay. Interesting things to look at from a pavement, and sometimes why it's worth it for our conceptual ideas, is that we can see cross-cutting relationships. We can see that probably the yellow ones form first. There's very few terminations into any of the other fracture sets by the yellow ones, so they were there ahead of time. The northeast set is parallel to the Laramide orogeny, so that's one of the big late Cretaceous, early Tertiary orogenic events in the Rocky Mountains that brought most of the Rocky Mountains up into a higher elevation. That was a northeast-oriented shortening event on the western continent of the United States, or the North American continent. And so that northeast set first forms is part of the Laramide uplift. The north-south set cuts through about 60% of the pre-existing fractures. And there's about 40% of those are terminating right against the northeast. So here's some examples. Like there's a termination here, termination, several terminations. Some of these are going through that, but they terminate eventually against a fracture set. And then the northwest set terminates against 80% of the northeast set and 40% of the north-south set. So these are all kind of filling in the space, but they're all terminating in that case. So from this kind of outcrop information, we can get the orientation statistics, length, termination, and insight into the origin and history of fractures. That's something we can do from that. What we want to do today is talk about what this might mean in a reservoir setting. For instance, if this was in the subsurface, what could it tell us? So we have to do a little bit of background work. And what I'm going to do here, I've taken all of these traces that I was showing before. They're all done in a GIS package, so that these are now actual lines, like fracture traces on a map. And what I want to do is I want to not just have this tiny linear kind of cigar-shaped outcrop exposure as my example. I want to calibrate this entire grid system that we're looking at here, the whole system, and fill it in based on the statistics that I can take from the simple one with this yellow traces. So I take this northeast set, this pink colored object is the outline of the outcrop. So that's my control calibration area. And then I want to do is I want to calculate the P32 intensity of that northeast set inside that. And that's what this figure is. And then I want to take that P32 and I want to distribute it to the entire block. So I'm using the same kind of intensity information here, and I'm distributing that through the whole piece so that I get information about the P32 inside this entire block. Now I can use this calibrated grid cell to build a fracture DFN model that I can then use for this exercise. Okay, so I'm using the outcrop to condition these blocks over here, right? So I use this information at the outcrop to calibrate these two pieces here. Okay, so this is just a quick reminder. This is rotated. So the northeast set here, and then I'm going to kind of move myself through. And now I've built fractures. These are the ones that I put in. I've now conditioned the model to recreate that, and it recreates it to an acceptable level of the intersections, the frequencies. So now I've got a bigger cube that I can work with. And now I'm placing two wells through this DFN model that's been calibrated to the outcrop. And what I'm showing here is well 1 versus well 2. So I've got a well 1 that's cutting across numerous fractures. It's designed to be perpendicular to the dominant northeast oriented fracture set versus well 2, which is designed to be parallel to that. And we want to walk through what that means, because that sometimes is a very important piece of trying to understand why fracture intensities might vary. It can be just as simple as the dominant fracture direction and the orientation of the well. That will give you a frequency count that's variable and different. So we've got inside the well calculator. We'll go to that in a second because I'll have to get out of this, but I want to just walk through the fracture sets. So the average strike is 40 degrees to the northeast, so 040. And in well one, this one cutting across here, where we've gone perpendicular to that fracture set, we have 344 fractures we intersected in this well. Okay, so and then the north-south set, that would be the red ones here. So with the yellow ones we have 344, red ones will have 86, and the northwest set we have 37. Okay, so these two wells enter the number of fractures northeast by well 1, appropriate cell, effective fracture permeability calculator. Do this for the two fracture sets. Okay, so let's get out of this piece. Let me what to end slideshow. Okay, take this. A little bit tricky, but we'll come here. So what I've done is I put 344 at the 40 mark. At 160, I put 86, and at 37, I put into the 130. Okay. Start with the simple assumptions that all fracture widths are the same. So 0.1 millimeters. So I've got that. All the widths, that's the apertures, are all the same. And then assume the average fracture height in a grid cell is 1 meter. So I don't want this to be impacted at all here. Fracture height is 1 meter, cell thickness 1. Remember, if that impacts that, we're not with the cell area on any matrix with multiplier. There's nothing like that. SH max doesn't matter. Shouldn't have any impact because I've made this all these multipliers. Yeah, I think that should work. It's always an interesting game. Okay, so now I'm going to go back and start with the simple assumption: vertical fractures, strike, slip, stress, assume stress, a constant with multipliers, assume a matrix of 0.1. So I have to put that back in, matrix 0.1. Okay. Assume a measured intrinsic permeability of 1500. That goes in. Here, that cell area. Okay. We are going to do an SH max of 50, even though it doesn't matter yet. Vertical. All right. So we're recording the orientation of the maximum effective fracture permeability, K max. So in this case, that's 32. Let me just jump ahead here to make sure I'm doing this right. 32, okay. Then I go back here. $32, $25, $39. Just to make sure I've got the right setup going. $25, $39. Okay. Just want to be sure we get the results that we're looking for by the end. Okay, so I've set this up, and we now can see that the things that we want to record in this little box, K max, for well 1, is that 25, 39 that comes from right here, the K max. And then the next piece I want to put is the K max strike of the orientation. The K max strike is 32. So that would go in this box right here. Okay. And then the K effective, what that looks like. K effective 1294. Just to make sure that looks right. 1295. Okay, good. And then the last piece that we're trying to put into that, sorry, to go back to this, is that would go here, K effective, and the K max K min ratio. So the K max K min ratio is about 3.85. Okay, so what we're looking at is if we record all those pieces, we start there. And we want to, that would be, okay, our fracture set, the fracture sets we've observed. And in this case, we're talking about no impact at all yet from the SH max orientation. So we've not critically stressed these fractures. These are all equally applied. They all have equal apertures. So basically, we're only looking at the orientation as it exists here for the impact on the permeability over here, okay? So this gives us basically the amount of anisotropy. So what we're seeing is that 344 outweighs the other off orientations. So the Kmax strike is 32 because these are mostly the fractures are at 40, and we these kind of averages out the rest of the way we go. And the maximum permeability strike, it's mostly following that dominant fracture set. So now we're going to do a little play on this and kind of work through the next pieces. So assume the fractures widths are proportional to the square root of the fracture length. That is, if the ratio of the lengths is 4:1, northeast to the northwest, or north-south, the ratio of the widths is 2:1. Modify the spreadsheet, assume the ratios for the northeast, north-south. So what do we do there? think we come in here and we want to then modify what that looks like. So we say, how did I do? That 4-to-1 and 2-to-1. So we come back to the spreadsheet and we say that that this one is 0. So when I've done that, I'm basically saying that in this case, let's assume that there is a preferential orientation based on aperture. So let's just, now we've taken the orientations to dominate the first part of the measurement we made. Now we're adding an aperture effect. What does the aperture effect do to those measurements? So now we're looking at the Kmax strike. In this case, the Kmax strike is parallel, or very parallel to the dominant set of the orientation, because we've applied such a large amount of width. The aperture is so great here at 0.4 millimeters that it's now said all of the fracture, all of the orientation, the permeability is parallel to that direction because it's so much more dominant. That's sort of the cubic law effect that we look at. We look at there's a big Kmax, and then our Kmax to Kmin ratio is very large, 60-to-1, just because we've put in such a heavy weighting on this aperture orientation piece. So we record that into our spreadsheet, to these pieces, and we're going to come back and then look at how that works through. Okay, so we're looking at that. I've got one of these orientations off because that's a little more. It's a little less than what we were looking at before, to see what's going on in that spreadsheet. I made this one. Yep. Okay. So what I had done is I have to make the same rules. I didn't add this in, so now I've made this 0.2 and 0.2 relative to 0.4. So these other two have the same kind of small effect. We're still dominant in this piece, and then all my numbers come together for that. Kmax, and then the Kmax Kmin ratio. It's quite large. And the effective permeability is very large, 29,000 millidarcies, or 29 Darcy. Okay. So that was the first part of this exercise. Now I want to go into the second phase of that, which is this well calculator, and I want to look at well 2. So well 2, if we remember, just go back to here really quick. Well 2 was this non-optimally oriented. It's more likely to intersect our white or red fractures than it is our yellow fractures. So we're going to come back over here and input that, and I'm just going to kind of walk through this one on the pieces. So what I've done for well 2, I've done the same count, and now because it's non-optimally oriented, I see a lot more of the north-south set, a lot less of the northeast set. And what we did in this case for well 2, because I want to speed up a little bit and make sure we get through this, is well 2 then has a Kmax just by having a different well orientation, the exact same fractured reservoir, but the orientation is different. Our measurements are quite skewed, quite a bit different in that regard. So the well 1 just by itself, now compare well 2 just by itself, our Kmax is maybe 1.5 Darcy to 2.5 Darcy, but the orientation of that is quite different. It thinks that it's 155, so that's like 155 sitting out here. Basically, that's what it thinks the maximum permeability direction is, because of all the red fractures that it's intercepted. And our effective is quite different, and our Kmax to Kmin ratio 5.2, not that different. But when we go to the next step, which is where we've added in, we know that, let's say we know that this this northeast oriented set has a higher aperture or a higher permeability. When we have this non-optimally oriented well with less of those northeast fractures in it, relatively speaking, we really miss that impact of that on this case. We go from 19 Darcy down to 2.3. So it's a significant difference based on how we've calculated this intersections in the well. We know that it's quite different in the directionality that we see, going from 155 to 17. And then looking at that from before, when we had the optimal well versus non-optimal well, we've got a 3.6 versus 1.6. And then here's that Kmax came in 27.5 to 2. Like, that's just so dramatically different, just because we've done a poor sampling of this from well 2 versus well 1. So that's something to keep in mind. And then the next part, I've taken these pieces in. Here's the answers. I thought I put those in there. Like that. There's the answer piece, what that looks like. Here's the answers to well 2, and then the well 2 new. One other aspect we've been talking about, critically stressed fractures, so that some fracture orientations are more likely to be propped open based on their relative orientation to the current day stress field. So what I did here is I went through and I put in the multiplier for critically stressed fractures. I put these different pieces in the same orientation, the same statistics as we had before for the number of intersections, but now I'm going to add a little bit of an influence to the critically stressed fracture pieces. And that's what the exercise kind of walks us through completely. But what we get to is that this is the critically stressed fracture effect. Okay, so if I am in the well 1 where I think all fractures are created equal, I say that my Kmax strike is 32. But if I said that the Kmax or the critically stressed orientation is parallel, or 50, nearly parallel to, are my dominant fracture direction, that's 40. The effect is that we get a permeability Kmax strike that is almost perfectly aligns with that, and our Kmax amount is dramatically increased in this regard, and our Kmax to Kmin is dramatically increased. Okay, so if in the perfect well, drilling the critically stressed fractures in the right orientation, you can have a very dramatic permeability uplift that you can see inside the well, inside for that. And this was really the basic argument of what we did when we drilled the critically stressed faults in Sumatra. Same idea. Now, one thing that's also interesting is that if we go through and say the poorly oriented well, but with critically stressed fractures considered, gives you almost the same effect as the zero effect reservoir. So if we keep all fractures equal, our Kmax to Kmin is the same as if we have calculated that with critically stressed component, but we have it in our poorly optimally oriented well. So well 2, while drilled in the wrong direction, still has something that looks very similar in its permeability field to that which we have no. Sometimes it's one of those pieces where if you consider the right thing, the right framework, you can still come back to nearly the right answer, or an answer that's acceptable. But it just highlights in this example the importance of looking at the impact of critically stressed fractures, or those that might have a permeability enhancement or aperture enhancement related to that. So that's what we're looking at here from this exercise.